Question number 6 for thin-walled cylinders. A pipe carrying steam at 3.5 MPa has an outside diameter of 450 millimeters and a wall thickness of 10 millimeters. A gasket is inserted between the flange at one end of the pipe and a flat plate used to cap the end. How many 40 millimeter diameter bolts must be used to hold the cap on if the allowable stress in the bolt is 80 MPa, of which 55 MPa is the initial stress? Next, what circumferential stress is developed in the pipe? So basically, this is your pipe carrying steam with this pressure with an outside diameter and wall thickness given. We have a gasket. So gasket is a thin piece of material used to seal two objects in contact. Okay, so very thin piece of material. That's your gasket. So now the question is, this is your cap, and it's being screwed by these bolts. So the question is, how many bolts do we need when the allowable stress in each bolt is only 8 MPa, and there's already an initial stress of 55? And then last, what is the circumferential stress in the pipe itself? Okay, so once again, we're looking for number of bolts and stress in the pipe. So in this scenario, the one carrying the stress here is not the cap, okay? It's more on the bolts, okay? The bolts are the one keeping the flange or the pipe and the cap together. So that's what we're looking for. How many bolts do we need? So first step, as usual, is still write out the given. Let's start. So first, stress, pressure, 3.5 MPa. Okay, P, 3.5 MPa. Okay, next, outside diameter 450 and thickness 10. So outside diameter, actually, it's specified. So let's call that DO for outside diameter 450 millimeter, and then thickness of your pipe is 10 millimeter. What else? Diameter of bolts were also given 40 millimeter. So let's call that DB for diameter of bolts. And then allowable stress is 80 MPa. So let's call that sigma A for allowable stress, or sigma max. And then there's already an initial stress of 55. Then let's call this sigma I for initial stress. Okay, anything else? No. Let's focus on the first part. Okay, we're looking for number of bolts. Okay, so to solve for that, let's first look at your allowable and initial stress. So once again, allowable stress is 80, of which 55 is the initial stress. So that means, okay, this system is already experiencing 55 MPa, even without the pressure in your pipe. Okay, so again, the cap already, or the bolts already carry 55 MPa. So that means, all right. Okay, so that means what we have now is only, so 80 minus 55, so that's 25 MPa to work with. Okay, so this means the bolts can only carry an additional 25 MPa of stress. Okay, so this is our reference, not your 80. Okay, and then again, this is stress in volts, right? And then what is stress? Stress is force in volts over area of each volt. Okay, so from this, we have an equation for the force experienced by each volt. Okay, so PB, again, force experienced by each volt, it's just stress times area of volt. Area of volt is the cross-sectional area of volt, so that's pi over 4 d squared. So pi over 4 db squared. Okay, so now what's the importance of that? That PB is equal to this. Okay, so essentially what's happening, so there's already your diagram or free body diagram for what's happening in the gasket or the pipe and your cap. So your pipe carries a pressure, right? That pressure creates a force on your cap, and that force is being resisted by the bolts. So that's why this is the free body diagram F, and then each force from each bolt. So therefore, if we use free equilibrium equations, we'll have summation of forces equals 0. Okay? And then F is to the left, to the right, P is to the left. So F minus P equals 0. Okay, wherein P is the total resistance of each bolt. Okay, so this is the summation of each reaction of each bolt. Okay, and then from this, F equals P. And again, F is the force created by the pressure in the cylinder or in the pipe. Therefore, the equation for that is the same as what we did in the derivation of the force for a pressure within a cylinder. So that's area times stress. Again, the area is the cross section of this, which is a circle. So that's pressure times pi over 4 diameter of your, the, to be more specific, the inner diameter of your pipe. Okay, so di, it wasn't mentioned before. So before, if you've noticed in the previous questions, it wasn't specified if the given diameter is inner or outer. It was just diameter. So that's why it's what we use. We assume that that is the inner diameter. Okay, but now it's specified this is outer diameter. Take note, what we need is the inner diameter. Okay, so that's di squared, then equals, this is the total force of each bolt. So therefore that's equal to N, which is what we're looking for, the number of bolts times the force on each bolt, which is this equation, right? So N times sigma B times pi over 4 dB squared, the diameter of bolt squared. Okay, next step is plug in our values. Okay, so P is pressure, 35 MPa. So we have, so our units should be Newton and millimeters. Okay, so 3.5 next times pi over 4 times di. So how do we get di? It's already shown here. Outer diameter is 450. So this entire thing is 450. Thickness is 10. So there's 10 on each side. Therefore, 450 minus 10 for the upper thickness, and then minus 10 for this edge. Inner diameter is 430. Okay, squared equals N. Sigma B is 25. Okay, that's what's left after the initial stress. So 25 times pi over 4. Okay, making sure everything is in MPa, Newton millimeter. And then times 40 squared. Okay, from this, please solve what's n. Right, it's 16.18. So good, Krishaline. So free us. I need the decimal first. So Krishaline and Edwin. So Mira and Frias. Frias. Okay. 16.19. Obviously, there's no 0.19 in volts. So say we always round up because anything less than 16.19 is not enough. So we round up, so that's 17. Okay, even if this 16.13 we round up, it's 17. Okay, so 17 volts. So take note of that. We round up for these types of questions. So that's part A. Let's solve for part B. Part B is what circumferential stress is developed in the pipe. Circumferential stress is the same as tangential stress. And you already know the equation for that. That's PD over 2T. So PD over 2T. So this is just a matter of direct substitution. Pressure is 3.5 MPa. Again, D is inner diameter. So 450 minus 10 minus 10, that's 430 millimeter over twice. And then T is still 10 millimeter. Okay, please solve. What's the answer? Correct, it's 75.25. Correct, Sierra. So Gutierrez and Vanessa. Stiliore and Gutierrez. Please give me the answer to two decimal places. Gutierrez. With 72.20, 75.25. The unit is N Newton per millimeter squared or MPa. Okay, that is number 6 for our thin-walled pressure vessel. Any questions for number 6? Please answer in the chat. How about the others? Please answer as well. Do you have any questions? Okay, great. So that ends our topic for thin-walled pressure vessels. On Saturday, we will have our modular exam. So coverage is everything up to thin-walled pressure vessel. Okay, so your quiz 1 plus thin-walled pressure vessel. Okay, so open notes, Zoom meeting, open camera. Do you have any questions or concerns? Okay, so for those who haven't answered your quiz number 1 yet, you have a week or you have until Saturday to answer it. Okay. All you have to do is send me an explanation letter. Details are in the orientation video. Please watch that and you may answer it anytime before or after you send the explanation letter. Okay? I haven't uploaded the answer key yet because not everyone has answered the quiz. I have to wait for everyone to answer the quiz first. All right? Okay? You don't have any concerns, clarifications? Okay. So that ends the lecture part for today.